Hello, guys. This is my first video lecture. Right. I don't know how this is gonna go, but I'll try my best to make this video readable. Okay. I'll be following the notes closely. Today we're going to do 2.1, 2.1, matrix algebra. So I strongly suggest you to just keep a copy of the notes by the video so we can follow this a little easier. All right, so we're going to start by talking about just some matrix that is n by n. That means it's in the dimension of m rows by n columns, right? And what they're going to look like is this, right? So matrix A is going to look like this, right? So you have entries row 1 column 1, entries row 2 column 1, and down to entries row m column 1. And then you move on to the second column, right? You have entries row 1 column 2, entries row 2 column 2, and so on, right? And m row column 2. Okay, and then you keep going until you hit row 1 column n, and then the last entry will be row m column n, right? So just some arbitrary matrix that we're working with that has the dimension m by n. And each of the entries can be named, right, using which row or which column they're in. For example, AM2, that is the entries in row M and second column. Okay. Now, 2.1 is matrix operation. We're going to look at how we can add matrices together. So adding matrices is very easy, right? You just add. So to add matrices by adding their corresponding entries. Corresponding entries. Okay. All right. So if we want to add matrices by adding their corresponding entries, that means they need to have the same dimension. Need to have same dimensions. Right. So you cannot add a 2 by 3 matrix with a 3 by 2 matrix, right? Later on, we'll do a little more practice with this. Okay. So if you look at theorem 1, we have A, B, C matrices with the same size, right? That's what it's important. We need them to have same size in order to add them together. And R and S are scalars, right? So if you look at 1, we have the commutative addition property, right? A plus B is the same as B plus A. Okay. So you can take a look at theorem 1 on your own. Nothing really tricky there. All right. So let's move on to below theorem 1. Let's take a look at this paragraph. When the matrix B is multiplied by vector x, it transforms x into the vector bx. All right. So what we have here is if I have a matrix B multiplied by some vector x, right? So here B is a matrix and x is a vector, that is a vector. Okay? And this is what we want to do. We want to learn how to multiply a matrix with a vector. Now, in a later section, we will learn about, in general, how do we multiply matrices together. But in this case, since we're talking about a specific type of multiplication, which is a matrix multiplied by a vector, we can rewrite that as a linear combination of the columns of B, which is like this: x1, b1 plus x2, b2 plus dot 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 plus xp, bp. Okay, something like that, right? This is what we did earlier. I think in chapter 1, we talked about linear combination using the columns of some matrix to perform multiplication. Okay, now moving on, by the linearity of multiplication by A, we get this, right? So we want to look at A times bx. Now, remember that bx is just a vector, right? So here, essentially, what we're doing is we're taking a matrix A multiplied by some vector B, some vector bx. And what we want to show here is essentially that we can rewrite that again as a linear combination of the columns of A. Right? So, but let's rewrite that first. So we have different entries from for bx, which is the above linear combination. So we can kind of do like a distribution. So multiply the vector A, the matrix A by bx, which is this, right? x1, b1 plus dot dot xp, bp. Right? All we're doing is doing substitution, replace bx with the linear combination that we have here. All right, and then we can do distribution. So we get A times x1 b1 plus A x2 b2 plus dot 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 plus A xp bp. Okay. Right. So here we can look at the vector A times bx is actually a linear combination of the vectors A times b1. Remember that b1, that's a vector, right? So A times b1 is a vector. That being said, we can rewrite this whole thing as a b1 x1, and put that in parentheses, plus a b2 x2 plus dot dot plus a bp xp. Okay, and by looking at this in a different way, right, we get that we can rewrite this as a b times x. So this is basically showing that matrix multiplication is associative, right? It doesn't matter how which order we do it in, but we actually have no tools on how to multiply A and B yet, well, except doing this, right? But each one of the A, B sub 1 is going to take you a lot of time to multiply. So again, we'll look at this, revisit this part in a later part of this chapter. Let's look at the definition on the last part of page 1. Right here, it shows you a basic idea of how to multiply two matrices A and B together. Right? But well, again, we're going to worry about that later. But let's move on to bottom to the beginning of page 2. Here we get a simple way of doing matrix multiplication by looking at each of its entries. Right, so let me clear the screen. Okay, it's too bright. All right, so here we go. Perfect. All right, so let's look at the top of page 2. And we want to look at the matrix multiplication AB. Okay, so to do this, we want to look at each of the entries of AB, right? IJ, right? The entries of AB in the ith row and the jth column is equal to AI1, B1J plus AI2, B2J plus plus AIN, BNJ. Right? So we do matrix multiplication by calculating each one of its entries. Now, to show you how this works, let's take a look at an example. So let's look at example 1. I'm going to leave 1 and 2 to you because they are just subtracting and adding. Now, let's look at example 1, part 3. So example 1, part 3, we want to look at E times C, which is -5, 3, multiply by 1, 2, -2, 1. All right, so remember the first thing that you want to check is, do their sizes match, right? So if you look at matrix E, this is a 2 by 1. And then the matrix C is a 2 by 2. Now remember that in order for matrix multiplication to work, these two numbers have to match, right? So no match in this case means can't multiply, right? So, you know, part 3 is pretty easy, right? There's nothing we can do here because the sizes don't match, right? So let's look at part 4, which is CE. So CE is flipping these two matrices. So I have 1, 2, -2, 1, multiplied by -5, 3. Now let's check again if their sizes match. Now this is 2 by 2. This is 2 by 1. Now in this case, they do match, right? These two numbers match, right? Match. And then by the outer two numbers, that tells us the size of the resulting matrix, right? The product, the size of the product of these two matrices, which is going to be a 2 by 1. Right? That's a 2 by 1. That means it's a column matrix with 2 entries. Right? Now our goal is to figure out what goes into these entries, right? So let's use the name of those entries, right? So this is, let's say, this is CE, right? The matrix CE, row 1, column 1, right? And then this will be CE, row 2, column 1. Okay? And then we can use these two entries and apply the formula up here. All right, so let me show you how. Let's go up here. Right, so first, we want to look at first row, first column. Right, so that means I and J in this formula will both be 1. Okay, so let's take a look at this. So first, I have A11 times B11, and then plus A12 times B12, right? Oh, B21, not B12, B21, okay, right? A11, B11, right here. A12, B21, right here. And then we just figure out what these numbers are and then plug them in. All right, but before we do that, let's figure out what the second entry is. So we're looking at row 2, column 1. So I is 2, J is 1. That means I have A21, B11 plus A22, B21. Now, since we only have 2 entries in here, right, we cannot go any further since n is 2 in this case, right? All right, so Let's go ahead. A11, B11. So A11 is right here. B11 is right here. So I have, oops, 1 times -5 plus A12, B21. So A12, that's a 2. B21, that's a 3. So 2 times 3. All right, next A21, B11. So A21 right here, B11 is right here, -2 times -5 plus A22, B21, A22, 1, B21, that's a 3, right? So 1 times 3. All right, and then you just calculate each one of these. So a -5 plus 6, that's 1. That's 10 plus 3, 13. Okay, and that's it, right? Let's check if the final size matches with what we started with, right? So we have 2 by 2 matrix multiplied by a 2 by 1. The middle two number matches. So the outer two number, 2 and 1, will be our the size of the result, which is a 2 by 1 matrix, which is what we have here, 1 and 13. All right, so that's good. And let's move on to theorem 2. So theorem 2, we are looking at, oh, sorry, give me 1 second. All right, perfect. All right, theorem 2, we're looking at having 3 matrices together and what type of properties we have. All right, so all these are pretty straightforward, right? Number 1 is the associative property. If you have 3 matrices multiplying together, it doesn't matter which order you multiply them. 2 and 3 are distribution. 4 is the scalar multiple, right? Again, very similar to associative property. And 5 is the identity property. Now, there's one thing that we want to point out. If you look a little below, we have 3 points that are not true, right? So matrix multiplication is not commutative, right? Meaning matrix A times B does not necessarily equal to B times A, right? Because A times B might be true when their size match, but if you flip over, the size do not have to match. If you look at our previous example, right, that's the case. Okay. Next, part 2, A times B is equal to A times C does not necessarily mean B is equal to C. Okay. If this is true, it doesn't mean that B is equal to C. Now, this has something to do with the matrix of A. Now, of course, if B is equal to C, then AB is equal to AC. I mean, that's fine. But this doesn't necessarily have to be true. Okay? And also, if A times B to matrix is equal to 0, this does not mean A is equal to 0 or B is equal to 0, right? So these 3 points are very different from our understanding of basic algebra, right? So, and that's what you have to be careful of. All right, next we identify powers of A, right? So that's similar to regular algebra. A to the k power is A multiplied by itself k times. Right? So that's pretty straightforward, pretty easy. All right. And last, let's talk a little bit about the transpose. Okay. So transpose is when the columns becomes the rows and the rows becomes the column. All right, so let me give you an example. Let's say A is the matrix 1, 2, 3, 4, 5, 6. Okay. Then the transpose of A, which is denoted by A to the power of this T, right? Some sort of symbol T. That means our first row is going to be our first column, 1, 2, 3, and our second row is going to be our second column, which is 4, 5, 6. There you go. Right? Pretty easy, right? So transpose, if you do some properties, if you perform transpose on the same matrix twice, then you get itself back, right? Because let's look at this. You do one transpose, that means the column, the rows becomes the column, and then you do that again, that means the first column is going to become the first row, second column is going to become the second row, right? So you do transpose twice, you get back to the same thing, right? Number 2, A plus B transpose is equal to A transpose plus B transpose, right? That's pretty straightforward. A simple proof can show you that. 3, R A transpose is equal to R times A transpose, right? So here, what we're doing is we're multiplying the scalar R with the matrix A first, and then take the transpose, which is the same thing as transposing A first, and then multiply by the scalar R. Or the transpose of AB is equal to B transpose times A transpose. Now, this is a very interesting fact. It can be proven, but it requires a little bit of work, but it's not that hard, right? All you do is you use the definition of matrix multiplication and then transpose to show that it's the same thing as this, entry by entry, right? But since we have limited amount of time on this video, I'm not going to show that. If we come back to class maybe in a few weeks, I really want to show you some of these theorem or properties using transpose. All right, so thank you guys. Hopefully this video was helpful. Please let me know through email or anything, right? If this video is helpful. Is there anything I can improve on? Maybe my writing. I know my writing is messy. I try to use different color, but it's a little hard. I'm still getting used to the pen pad and pen casting video recording. All right, but feel free to email me, and don't forget to join office hour every Tuesday and Thursday from 1 to 3. Have a good day.